Hello friends, welcome back to our course on General Relativity. This is part 3 of our discussion on special relativity. Today, we shall derive the theory of classical electrodynamics purely from the principle of relativity. In particular, how charges respond to an electromagnetic field. This is the first part of 2 on our derivation of the fundamental equations of electrodynamics from relativity. Here are the references for this course. You can find the links to these books on Amazon in the description below. These are the topics we shall cover. We are going to derive the Maxwell's equations and the Lorentz force from the principle of relativity. The Maxwell's equations tell us how charges generate electromagnetic fields, while the Lorentz force governs how a charged particle responds to an electromagnetic field. Together, these two sets of equations form a complete picture of classical electrodynamics. To achieve this, we first give a quick review of the principle of least action, starting with the simple example of the Newtonian mechanics of a single particle. We will show how the Newtonian equations of motion can be derived by requiring that a functional, known as the action, be extremized by arbitrary variation of the particle's trajectory. This will be clear in a moment. Next, we show that the same could be done with a relativistic free particle and make connections with Newtonian mechanics in the non-relativistic limit. Finally, we construct the simplest interaction to the relativistic particle by introducing a vector field which couples with the particle in the way required by relativity. These three elements will lead to both the Maxwell's equation and the Lorentz force law. As a result of such simple considerations, we shall discover the gauge invariance of electrodynamics, as well as the conservation of electric current. In this lecture, we discuss only the Lorentz force and will complete the derivation of the Maxwell's equations in the next lecture. Let's start with Newtonian mechanics. This is the equation of motion of a single particle in a potential. The gradient on the right-hand side of this equation is the force. This is just Newton's second law. The degrees of freedom of the particle are the three functions of time describing its trajectory. Forces of this kind are known as conservative forces since they conserve the energy of the particle. When solved, the equation of motion gives us the trajectory of the particle in time. This equation is a vector equation and is taken as a postulate in Newtonian mechanics. But there is actually an alternative to this formalism, in which the equation of motion is derived from a more fundamental principle. We are talking about Lagrangian mechanics, and the principle in question is the principle of least action. The action is an integral over the trajectory of the particle of its kinetic energy minus its potential energy. X dot is the velocity of the particle, where the dot notation represents time derivative. The action S is a functional of xt, since it takes in the entire trajectory from t1 to t2 and spits out a number. This action allows us to pick out the physical trajectory of the particle, which is defined by the solution of the equation of motion. The physical trajectory is the one which extremizes the action, such that if we introduce an arbitrary variation in this trajectory, the associated change in S to the first order in delta x should be zero. This variation is taken under the condition that the boundary values of x is fixed, that is, the function delta x at the endpoints t1 and t2 must be zero. This is the principle of least action, or more accurately, extremal action, according to this equation. Things will become clearer if we work out the variation of s explicitly. We simply take the variation with respect to the function x under the integral. Here comes a step that we shall often use. The time derivative in this term can be shifted from delta x to x dot by incurring a minus sign. This is simply the result of the product rule of derivatives, as well as the boundary conditions which allow us to drop the total derivative. Since delta x is an arbitrary variation, we can choose it to have support only at a specific time t, while being zero everywhere else within the interval t1, t2. This equation implies that the expression within the brackets is equal to 0 at time t. T could be any time within the interval. This equation is just the equation of motion for a single particle in a potential from Newtonian mechanics, which is now derived as a condition for the variation of the action to be zero. In other words, the physical trajectory which satisfies the equation of motion is also one which extremizes the action. Let's do some dimensional analysis. The action has the dimensions of time times energy. Keep this in mind as we move along when constructing the actions for physical systems. The Lagrangian formalism is quite general and can describe any number of degrees of freedom. The integrand of the action is known as the Lagrangian. Here, we have assumed that the Lagrangian depends only on the coordinates q's and their time derivatives. These q's constitute all the degrees of freedom of the system, and all the time dependence in L is implicitly carried in the q's. That is, L does not have any explicit time dependence. Such a time dependence would violate the time translational symmetry of the action. Here's why. First, let's set the time interval to range over all times, as we could use the explicit time dependence of L to restrict its support to between t1 and t2. Now, let's shift all the trajectories in time by the same amount delta t. If the laws of physics is invariant under time translation, then the action should be invariant under such a translation as well. But it is precisely this explicit time dependence of L that violates the symmetry. Now let's vary the action with respect to Q. The variation of L is the result of the variation of Q and Q dot. As before, we can shift the time derivative on delta Q in the second term to the rest of the product, incurring a minus sign, due to the requirement that the boundary conditions are preserved. This variation of S should be zero. Since delta Qi is arbitrary, the expression in brackets is also zero. This is the equation of motion, also known as the Euler-Lagrange equation. Now is a good time to discuss the consequence of symmetry in the action. The symmetry is defined by the transformation of Q to Q prime. An action is symmetric if it is invariant under this transformation. This invariance implies that if the solution Q extremizes the action, so will Q prime. This means both the first-order variation of S with respect to Q or Q prime must be equal to 0. In other words, if Qt is a solution of the equation of motion, so is Q prime t. Now we are ready to find the action of a relativistic free particle. Recall that from the last lecture, the trajectory of a relativistic free particle, x lambda, must satisfy this equation of motion. The equation takes this form if the curve parameter lambda is an affine parameter. This is what we have derived in the last lecture. See the link in the description to refresh your memory. Let's reverse engineer a suitable action that could give rise to such an equation of motion. We can try the most obvious choice. An important constraint is that the Lagrangian must be invariant under Lorentz transformation, that is, it is a scalar. This is so that the Lorentz transformation of any solution of the equation of motion is also a solution. We can easily see that setting the first-order variation of this test action will give us the desired equation of motion in the yellow box. Again, we can shift this lambda derivative to the other term, incurring a minus sign, by using the boundary conditions. Indeed, this gives us the correct equation of motion. Since this is a vector equation, the Lorentz transformation of the solution is also a solution. This is the direct consequence of the Lorentz invariance of the Lagrangian. In general, a Lorentz invariant Lagrangian will give a Lorentz covariant equation of motion. But we can do better than this. Let's take a square root. Assuming that the trajectory is time-like, we must include a minus sign, so that we are taking the square root of a positive quantity. The reason for taking a square root is so that d lambda in the denominator will be of the same power as d lambda in the numerator. In this way, our action will be invariant under the change of curve parameter. Remember what we have emphasized in the last lecture. What's important is the curve in space-time. Different curve parameters could be used to describe the same curve. So it makes sense for our action to be invariant under this change of parameter. Let's include a factor of mass m of the particle and c the speed of light so that we get the correct units for the action. To see why, we can use the fact that the action is invariant with respect to the choice of lambda and choose lambda to be t. This can be compared to the Newtonian action, which has units of time times energy. This comparison actually goes further, because with these prefactors, the non-relativistic limit of the relativistic action actually approaches the Newtonian version as we go to low velocities. Let's verify this. Writing out this square root explicitly, using the fall velocity, and the Minkowski metric, we have v is just a regular tree velocity. We can expand this explicitly in powers of v over c as in the last lecture. Compare this with the Newtonian case. This just reduces to the action of a non-relativistic particle traveling in a constant potential, which is its rest energy. Thus our action for the relativistic free particle has the correct non-relativistic limit. Let's switch back to an arbitrary curve parameter, lambda. Let's vary this action to get the equation of motion. This is the variation of the square root term. This gives the following variation of the Lagrangian. We can shift this lambda derivative to the term in brackets by absorbing the minus sign. This leads to the following equation of motion. Let's save this variation of the action for later. This equation of motion does not take the simple form from earlier. This is expected, since in general, lambda is not an affine parameter. We have discussed this extensively in the last lecture. Notice that there are exactly 4 equations of motion, which could be solved for the 4 functions of the trajectory. Also notice that this term in brackets is a normalized time-like vector. Multiply this by c, and we get a vector with the following invariant magnitude, which is identical to that of the forward velocity dx d tau. We can easily show that the vector u is in fact just the forward velocity, or in other words, n is equal to the forward velocity over c. This is because the square root term is just d lambda d tau over c, as we can see from the definition of tau. Which implies that if we multiply the equation by d lambda d tau, we will get the familiar form of the equation of motion with tau as the affine parameter. Which means, if we take the solution x lambda and take lambda as a function of tau, this would satisfy the equation of motion in the red box. Even though this function, lambda of tau, is completely arbitrary. This amazing fact is due to the parameter invariance of the action, and as the result of the equation of motion itself. We can use this unconstrained function lambda of tau to satisfy the velocity constraint in the blue box. Thus once again, the number of equations matches the number of functions to solve. We could also look at this in another way. We could invoke the parameter invariance of the equation of motion right from the beginning, and choose lambda to be equal to tau. This equation of motion then becomes the familiar one for an affine parameter. But from this perspective, it is less obvious why the constraint in the blue box will be automatically consistent with this equation of motion. A situation in which this is even less obvious is when there are interactions, which will result in a force term on the right-hand side. Why should such an equation of motion, which may be very complex in general, preserve the velocity-magnitude constraint? If you will recall from the last lecture, in our discussion of the accelerated particle, we have to be careful how to set the equation of motion, so as not to over-constrain the solution, in order for the condition in the blue box to be satisfied. Now in our parameter-independent formalism, as long as we construct our action to be lambda invariant, we will naturally have the degrees of freedom to satisfy both the equation of motion and constraint. We shall now go through an explicit example of the interacting case. Let's derive the Lorentz force law, which governs how a charged particle responds to an electromagnetic field. Let's try and introduce an interaction term to the action of the relativistic particle. In order for the action to be Lorentz invariant, its Lagrangian should be a scalar, and the only vector attached to every point of the particle's trajectory is its gradient. And we would need another vector to form a scalar with this. Let's call this A. This is a vector field which interacts with the particle locally, that is, where the particle is located. This is the condition of locality, which means no action at a distance. The other condition is that we must preserve parameter invariance, as before. This is the simplest interaction we can introduce to the relativistic particle, which satisfies all these constraints. For this lecture, we need not worry about the dynamics of the vector field A. Just assume that it is some background field applied to the particle. That is, although this field can change in space-time, it is not affected by the motion of the particle. We shall deal with the action of the A field itself in the next lecture. Let's look at the Lorentz transformation of the A field more closely. This is the transformation of the particle's coordinates. Here we shall treat this change as an active transformation. That is, the change of the particle's coordinates is actually due to the particle being moved to the new location, and not due to a change of coordinate system. The vector field A transforms in the following way. Being a vector, its components is just transformed by lambda. This is straightforward. The transformation of its argument requires further explanation. We can think of this as actually moving the field. Why this inverse lambda can be understood with a simple example. Let's just look at the translation. The translation of a point x by A is just shifting its position by A. While the translation of a function fx as an active transformation should proceed as follows. The whole function is shifted by A, turning fx to fx minus A. Notice that the change of the argument of the function is the inverse of the transformation of a point under the same translation. For the same reason, this is why we have the inverse lambda in the argument of A. In contrast, a passive transformation is a change due to the change in coordinate systems. Much of our discussion on general relativity later on in this course will be based on such transformations. Thus, if we have the location of the particle in the argument of the field, this should transform as the combination of these two transformations. And the lambdas in the argument of the field cancels. One could see that under these two transformations, the Lagrangian of the interaction term is indeed Lorentz invariant. Let's include a coupling constant Q, which determines how strongly a particle is coupled to the field. as well as a factor of c. This is included partly due to convention, and also such that we have the right dimensions for an action. Let's do some dimensional analysis. We require Q times A to have dimensions of energy, so we treat A as some kind of potential, while dx over c has the dimensions of time. The parameter lambda need not be considered since we have equal factors of it in the numerator and the denominator. Indeed, these give the correct dimensions for an action. Now let's examine this interaction term exclusively and calculate its variation. Let's calculate the variation of this expression with respect to the particle's trajectory. In this second term, we can once again use the boundary conditions to shift the derivative lambda to the other term, adding a minus sign. The goal is to factor out delta x, which is arbitrary. Here, we introduce a simplified notation for the derivatives with respect to x. This works exactly like a vector, and we can raise or lower its index with the metric tensor. And they have exactly the Lorentz transformation properties you would expect. The lower index object transforms like a covariant vector, while the upper index version is like a contravariant vector. We shall work out the details of this in a moment. For now, let's continue to calculate the variation. Notice that we have lowered the index of delta x to match the second term in order to factor it out. Let's switch the dummy indices mu and nu. For the second term, we can once again use the chain rule. We are now ready to look at the variation of the total action to get the equation of motion. The variation of the free term gives, this is our earlier result, while the variation of the interaction term is what we have just calculated. Their sum must be equal to 0. Delta x being arbitrary means this term must be equal to 0. This is the equation of motion, which is in fact the covariant version of the familiar Lorentz force law, as we shall see. Once again, we have 4 equations of motion to solve for 4 functions, which give the trajectory of the particle. As before, we could let lambda be a function of tau, which could then be used to satisfy the velocity constraint in the blue box. Taking the tau derivative of x and using the chain rule, as mentioned earlier, d lambda d tau is just equal to this square root term. The result is just what's in the brackets above. And when we multiply both sides of the equation by d lambda d tau, this just becomes which is satisfied by our composite function, which also satisfies the velocity constraint. Thus these two equations are automatically consistent with each other. This is always the case if we construct our action to be invariant under the change of the curve parameter lambda. Here's what we mean by a parameter invariant action. For the general curve parameter, the action looks like this. And we can express this in terms of a different parameter, tau, in the following way. Whereas if we have chosen tau to be the curve parameter right in the beginning, we should get this. The action is invariant under the change of parameter if these two are equal. This invariance means the action functional of x of lambda is equal to that of the case which lambda itself is a function of tau. Demanding the arbitrary variation of the first form to be zero, we get this equation of motion, which is a vector equation. This has the solution x lambda. Whereas if we take the arbitrary variation of the second form to be zero, we should get this equation of motion, which is just the previous equation, but switching lambda for tau. But since these two actions are equal and share the same extremal value, the solution we get by expressing lambda in terms of tau should also satisfy the second equation. Since lambda is a general parameter, it is an unconstrained function of tau. This is what we use to satisfy the velocity constraint. As you can see, this scheme works in general, as long as the action satisfies the parameter invariance that we have defined here. However, if we were to just look at these two equations, it is not at all obvious that they are consistent and could be satisfied simultaneously. Let's check explicitly that the velocity invariant is actually a constant, conserved by the equation of motion above. Taking the time derivative, we have we can use the above equation to evaluate this. The right-hand side is zero, since the A field term, which we now formally name the field strength tensor, is anti-symmetric. This is zero because the indices mu and nu on the velocities are symmetric under exchange, and thus their contraction with the anti-symmetric f mu nu must be zero, which means the time derivative of the velocity invariant is also zero. So the constraint below is really preserved by the equation of motion and is thus consistent with it. This would look like a very lucky accident if we had not known about the parameter invariance of the action. This equation tells us how a charged particle responds to an electromagnetic field. It is the covariant version of the familiar Lorentz force. This is a vector equation under Lorentz transformation, as both the particle's acceleration and velocity are vectors, and as we shall show now, f mu nu is a tensor. Let's look at how f mu nu transforms under Lorentz transformation. First, we need to figure out how the partial derivatives transform, specifically how their upper index counterpart transforms. Let's work out some useful identities. If lambda is the Lorentz transformation from the unprimed frame to the prime frame, partial x prime partial x would just be the matrix lambda. While from the chain rule of partial derivatives, we have. Thus we see that partial x prime is just the inverse of lambda. Now let's relate partial sigma prime to the unprimed frame, again by using the chain rule. By the identity above, this is just lambda inverse. Thus we see that the lower index partial derivative transforms just like a covariant vector, as expected. Recall from lecture 1, lambda inverse is just equal to lambda with its upper index lowered and its lower index raised. From this, we can see how the upper index derivative transforms. Now express this in terms of the upper index derivative. First we write this as a contraction with the Kronecker delta. This delta is equal to the product of two Minkowski metric. And we can use one of them to raise the index of the derivative, while this term just gives us back lambda. As expected, the upper index derivative transforms like a contravariant vector. Now let's see how A transforms. Previously, we have considered its Lorentz transformation as an active transformation. Now we would like to treat its transformation as a change of coordinate system, that is, a passive transformation. The active transformation is the change of a function under the same coordinate system. Under a coordinate transformation, the argument of A also changes to x prime. This cancels out the inverse lambda. Actually, we have done things in the reverse way. Usually, the Lorentz transformation of a vector field as a coordinate transformation is defined like so. Then we take away the prime in the argument of the field and just look at how the function is transformed. For much of this course, we shall deal mostly with coordinate transformations. Now, let's see how f mu nu transforms. This is quite straightforward, since A and its derivative transform independently, as lambda is constant. Let's look at the transformation of the first term. For the second term, just switch the indices mu and nu. Then switch the dummy indices alpha and beta. Now the lambdas could be factored out. Taking the difference of these two, we have thus f mu nu transforms like a contravariant tensor under Lorentz transformation. Later on, while dealing with general relativity, we will find that f mu nu actually transforms like a tensor even under general coordinates transformations. This is due to some cancellation that occurs between these two terms. But that's for later. Thus we have verified that the Lorentz force law is really a vector equation by showing that f mu nu is a tensor. Now let's uncover the gauge symmetry of electrodynamics. The key lies in how the vector field interacts with the charged particle through only the combination f mu nu. In practice, we can only make measurements on the A field by observing its effects on the charged particle through the Lorentz force law. Thus one could say that the only physically relevant object is the tensor f mu nu. There is a rather obvious symmetry to this tensor. Notice that if we were to add to A the derivative of some arbitrary function, this does not change the resulting f mu nu tensor. This transformation is known as a gauge transformation, and we say that the field strength tensor is gauge invariant. Since they give the same f mu nu tensor, the A field and all its gauge transformations are physically equivalent. This is an important point. This symmetry will help us construct the action of the A field in the next lecture. Next, we shall extract the electric and magnetic fields from f mu nu. First, let's write the acceleration on the left-hand side as the first derivative of 4 momentum. This will match the first derivative on the right-hand side. In this way, multiplying both sides of the equation by d tau dt will give us the equation of motion in terms of t, the lap frame time. This is usually the frame in which the equations of classical electrodynamics are written. We shall separate the components of f mu nu into two groups. The first, with one time and one spatial indices, and the second, with both spatial indices. We need not look at fi0 separately, since it is just a negative of f0i, due to the anti-symmetry of f. The electric field is defined to be f0i. This is regarded as a vector with one spatial index, while the magnetic field is the contraction of the epsilon symbol with f, also forming a vector with a spatial index. Since both the electric and magnetic fields by themselves are not Lorentz vectors, we are not concerned about where we place their indices, whether upper or lower. They are in fact the same things. Our convention of the Minkowski metric also helps to avoid many confusions, since we have adopted the mostly positive signature. Therefore, for the spatial components, the raising or lowering of indices do not affect their values. Due to the anti-symmetry of the epsilon symbol, this last expression can be further simplified. Now you see why we have added the factor of half. This is just the curl of A from vector analysis. The B field is defined to be the curl of A, and in components form. Let's examine the spatial components of the equation of motion above. Expanding out the sum over the index nu, we have this term is just minus c. The minus sign comes from the lower time index. And we can write fi0 as minus f0i to make connection with the electric field. The second term involves the magnetic field. We would need to write Fij in terms of B. Let's invert this relation below. B is a single index object, while F has two indices. So it makes sense to try a contraction with a three-index object, the epsilon symbol. Here, we can use our old friend from the last lecture, the epsilon contraction identity. Evaluating all the delta symbols, we have again, using the anti-symmetry of F, we have our result. Substitute this back into our equation. And doing some rearranging. This is just the cross product of velocity with the magnetic field. We have recovered the familiar form of the Lorentz force from the undergraduate E&M course. In this lecture, we are using the Heaviside Lorentz units for electrodynamics. This is often favored by particle physicists due to the simplicity of its formulae. According to this system, the electric and magnetic fields share the same units, while charge times electric field has the units of a force. We shall have more to say about the different units of electrodynamics in the next lecture. What about the component mu equals 0? We need not consider the time component because the velocity constraint, or equivalently the momentum invariant, will give us the time component of momentum. Once the spatial components are solved, now we shall identify the conserved current of electrodynamics. To talk about something like an electric current, we must first modify our discussion of a single charged particle which is under the influence of an electromagnetic field to many charged particles that could form a distribution or current. Let's choose lambda to be the proper time of a charged particle. For many particles, we simply sum each of their coupling to the same vector field, but assuming each particle to have its distinctive charge, mass, and proper time, labeled by the index n, which is the particle index. This is not an oversimplification, because as we shall see in the next lecture, each particle could form a source of the electromagnetic field, and it is through the same field that the charged particles interact among themselves. Of course, we must also sum over all the free particle actions. Let's focus on the interaction term. From this, we shall derive another vector field. This is what is known as the electric current density. Its meaning will be clear in a minute as we work out its properties. Essentially, we want to write this interaction of charged particles with a vector field as the interaction between two vector fields, one of which is the current density J. This term is an integral over space-time, which will make sense for an interaction term for two vector fields, which by definition are continuous functions over space-time. As a first step towards our goal, let's change the curve parameters to the coordinate time, describing the time displacements on the trajectories of each particle. To be more accurate, when we write xt here, what we actually mean is this. We are sacrificing accuracy for simplicity of notation. The next step is crucial. In expressing this as an interaction between two fields, let's introduce the Dirac's delta function. Take some time to look at this expression. It is easy to see that this is equal to the preceding expression. First note the argument of the A field. They are now the spacetime variables of the new spacetime integral. Evaluating the new time integral, this time delta function will replace the new time variable with the individual time coordinates of the particles, as in the preceding expression. While performing this spatial integral, the spatial delta function will replace the new spatial variables with the actual positions of the particles at time tn along each trajectory. Thus performing the spacetime integral over the new variables tx will restore the new expression to the previous line. This expression, which is a function of the new spacetime variables tx, is the electric current density. Usually, we will just write this integration measure as d4x. Now the question is J really a vector field? A vector field transforms on the Lorentz transformation in the following way, with the A field as an archetype. Let's verify that this is also how J transforms. For this purpose, it is more convenient to use the proper times of the particles as the curve parameters. This is J described in the frame of O, the unprimed frame. While in the frame of O prime, we just replace all the unprimed coordinates with prime coordinates. The prime system is related to the unprimed system by the Lorentz transformation lambda. Of course, all the proper times remain unchanged. Let's work out if these two are related by the correct transformation rule. First, let's write this time component delta function as a x0 delta function. By using the scaling property of the delta function in the yellow box. The reason we do this is due to the simple way Lorentz transformation works for this set of coordinates. These two delta functions then form a four-dimensional delta function. Let's do the same for the delta functions in the O frame. We claim that this 4D delta function is in fact Lorentz invariant. That is, its value is the same, regardless if we insert into its argument the prime or unprimed variables. Let's prove this. The key is starting with the integral representation of the delta function. This is a relativistic dot product. K is a 4-vector, and its components are the integration variables. The range of the integrals runs from -infinity to infinity. Replacing the argument x with x prime, we have. Since this dot product is invariant under Lorentz transformation, let's apply the inverse transformation to both its elements. Effectively, this transfers the transformation from x to k in the form of inverse lambda. Now we use the fact that the integration measure, d4k, is Lorentz invariant. It is easy to see this by calculating d4 lambda inverse k. It is related to the original measure d4k by this Jacobian, which is the absolute value of the determinant of the matrix lambda inverse. Recall from lecture 1 that the determinant of any Lorentz transformation is equal to 1. This has to do with the invariance of the Minkowski metric under Lorentz transformations. This means the measure is invariant. Thus we can replace d4k by d4 lambda inverse k. Doing this just means that we are merely changing the integration variable to k prime, which doesn't change the result. Thus the delta function is indeed invariant under Lorentz transformations. So we can make this replacement of delta function. All that remains is this fall velocity, which is related to its unprimed counterpart by a simple Lorentz transformation. Compare this to the current density in the O frame above. We have our result. The electric current density does indeed transforms as a four vector. Therefore, this form of the interaction action is also Lorentz invariant, as we can easily see. This integration measure is also Lorentz invariant, since it is just related to the earlier Lorentz invariant measure by a factor of 1 over c. Thus this new form of the interaction action is also Lorentz invariant, as it should be. Another important feature of this current density is that it is also conserved. Let's prove this. As we move along, you'll see what we mean by current conservation. To begin our proof, let's evaluate this integral. This delta function will replace all Tn with t. This is the time at which the current J is specified. Let's now examine the components of J, starting with the time component. What does J0 mean? If we measure J0 at point x in spacetime, this delta function is non-zero only if a particle happens to be located at the spatial location x at time t. This means J0 of x is non-zero when there is a particle at x and is zero where there are no particles. It is therefore similar to the particle number density, or more accurately, the charge density. We can see this directly. First note that this derivative just evaluates to c. Thus J0 becomes we will see that this term in the red box is the charge density. It has all the right properties for a charge density. For instance, if we integrate it over any spatial volume. This integral within the sum is not zero only if xn, which is the spatial location of particle n, is in the volume, and is equal to 1. This sum is over all the particles that are in the volume V at time t, and is the total charge contained in the volume. Thus we see that the term in the red box is indeed the charge density. The spatial components of J is given by. Together, we can write the 4-vector J as follows. This current satisfies what is known as the continuity equation, which is the reason why we say that it is conserved. This goes as follows. First, let's take the time derivative of the charge density. The only place for this time derivative to act is in the arguments of the particles' trajectories. We can use the chain rule. Notice that this derivative is just equal to the negative of the derivative with respect to x, since they both appear in the same way in the argument of the delta function, except for a relative minus sign. This gives the result. Since this derivative will act only on x in the delta function, we can bring it out of the expression entirely. Compare this with the expression above. This is just the spatial component of the current. Thus we have the negative of the divergence of the tree vector J. This is the continuity equation. To understand what this equation says, let's integrate both sides over some volume. The red box on the left-hand side is the total charge in the volume. Q depends only on t, so let's replace partial t with a total derivative. On the right-hand side, we can use the divergence theorem, also known as the Gauss theorem. d sigma is the surface element of the volume, and n is the vector normal to the surface. This term is then the total current flowing out of the volume through the enclosing surface, with J as the tree current density. The current should be negative the rate of change of the total charges in the volume if charge is conserved, which is precisely what we get. Therefore, we can take the continuity equation as a statement of charge conservation. We know that the vector J quantifies the flow of charges because it is proportional to particle velocities and is non-zero only where there is a particle, again due to the delta function. If we have integrated over all space, then the surface integral should be zero, assuming that all fields go to zero at infinity. Q will be the total charge at time t. Thus the total charge is conserved. We can write the continuity equation in a more covariant way. This equation is often synonymous with current conservation. There is a connection between the gauge symmetry of this action and the conservation of charge. Taking the gauge transformation of this, leads to this extra term, which can be written in this way using the product rule. This total derivative can be evaluated to give a boundary term. We can drop this term if we assume that all fields go to zero at infinity. Thus once again, we can shift the derivative from one term to the other by including a minus sign. And this extra term is zero if the current is conserved. Thus the action describing the coupling of an electromagnetic field to an electric current is gauge symmetric if the current is conserved. These are the key results of this lecture. In the next lecture, we shall derive the Maxwell's equations, which govern the dynamics of the electromagnetic field.